Hello and welcome back to the video of my channel. I'm underscore AXE. Today we're going to add more factors, multiples, prime numbers, prime factorization, LCM and GCD example problems. And some of these may be challenging for you, and just keep that in mind. And that's all I have to say, and please subscribe to my channel and enjoy the video. Thank you. Here's question 1. For part A, for part 1 of part A, we need to find the mean or the average of the first 5 primes. Notice that the first 5 primes will be 2, 3, 5, 7, and 11. And we can divide this by 5 to get the mean. And you'll get an answer of 5.6. Hence, find the LCM and GCD of those 5 primes. And since we know all of these numbers that we have chosen are all primes, those 5 primes are what we are called the term coprime. And the word coprime means that all of those numbers only share a common factor of 1. And with that, we can conclude that the GCD of those 5 primes will be equal to 1. Which means, or we can just find that the LCM is equal to the product of all those primes. So it will be 2 times 3 times 5 times 7 times 11. Notice that these two answers can be found manipulatively by doing the LCM and GCD method using prime factorization. Now if you're wondering what the value of the LCM is, it will be 2310. Alright, for part B, this is a bit interesting. It is given that 2 primes are added to get 25. Find the product of those 2 primes. So let's just set up an equation like so. Notice that 25 is odd. And what parity of number plus what parity of number gives an odd number? And the answer will be to which one to be odd and the other one to be even. Or both can be switched, whichever you would prefer. But notice that since 2 of these numbers are primes, therefore we have an odd prime plus an even prime gives 25. But notice the only even prime that exists is 2. You can actually check that, because any other number would have like more than 2 factors. So 2 is the only even prime here, and therefore we can solve that the odd prime will be 23. Therefore our product will be 2 times 23, which will be 46. Number 2 is quite challenging. So it is known that the LCM between 60 and x is 420. How many values of x satisfies the equation above? So let's just set up our prime factorization way of finding the LCM and GCD. So for 60, when expressing the prime into its prime factorization will be 2 squared times 3 times 5. We don't know about x yet, so we just leave it back there. And when we know that the LCM is 420, and it's expressible as 2 squared times 3 times 5 times 7. Notice that we have a factor of 7 in the LCM, but we don't have a factor of 7 in 60. Therefore, x must contain at least a factor of 7, otherwise the LCM wouldn't contain a factor of 7. Alright, so let's see what we can observe here. So let's just first observe this base 2 column. Notice that the LCM would be 2 squared, and we have a 2 squared as a 60, and therefore x could the factor of 2 can be 2 to the 0 or just 1, or it doesn't contain a factor of 2 at all, or 2 to the first. That also works, since we can choose the greatest power, or 2 squared. We can choose either of these. Notice that if you choose its power to be bigger than 2, it will ruin everything, because we must force this to be equal to 3, which will again ruin the question's criteria. So for the possible values of the power of 2, we have it could be 0 to 2, therefore we have 3 ways. Now let's see for the power of 3. Let me just erase that. Let's look at the power of 3. We can do the same thing right here. But since we have a 3 as a factor of the LCM, and then we have a 3 as a factor of 60, therefore the power of 3 could be 0, or it doesn't contain a factor of 3, or it could be 1, since we can pick either of these. So therefore, from the factor of 3, we have the possible power values to be 0 and 1. Therefore, we have 2 ways. Finally, for the power 5. We can again observe that the LCM has a factor of 5, and 60 also has a factor of 5. Therefore, the power 5 in x could be 0 or 1 by the same reasoning before. Therefore, for the factor of 5, it could be either 0 or 1, which we have 2 ways. Now for the total possible values of x, we can just multiply all of these together. So the total possible values of x will be 12. So this is a very interesting way to mash in the LCM and GCD and combinatorics. For part B, it is given that the GCD of y and 45 is 3. Find the smallest possible y that satisfies the criteria above. We can rewrite 45 as 3 squared times 5, and we don't really know about y yet. We can rewrite 3 as 3. Notice that 5 is not chosen here in the GCD. Therefore, y could not contain a factor of 5. However, it does contain a factor of 3, and therefore this really forces us to pick that y must be equal to 3, since we're choosing the least power right here, which is exactly 3. However, notice that you can add a factor such as 7, because we can choose the smallest factor to find the GCD. So for example, let's say we choose a factor of 11, for example. 5 is not chosen right here, since we can interpret this as 5 to the 0, and then we can pick that. We can also interpret this as 11 to the 0, and then we can pick this. And of course 11 to the 0 is just 1. Notice that this always works for every prime. So let's say we pick 23, it will also work. However, the question is asking us to find the smallest possible y that satisfies above. So therefore, there will be no multiplication of other primes that are kind of messing around the value of y. So hence, the smallest possible value of y is 3. Number 3 is a challenging one with an extra twist. Andy and Ben are playing a game. Andy would choose an element from the set X, which contains the elements 2, 3, 4, 5, 6, 7, 8, 9, 10, while Ben would choose an element from the set Y, which contains 4, 5, 6, 7, 8, 9, 10, 11, and 12. And with these two chosen numbers, they will calculate the greatest integer that divides both of the chosen numbers. How many possible combination pairs are there? And what I mean is how many possible combinations of the chosen numbers are there. Notice that the number of elements in set X will be, let's see, there will be 9 elements, which is also equal to the number of elements in set Y. So therefore, the number of possible combinations are there. Well, notice that we choose exactly one element from X, so therefore we can have 9 possible choices for any to choose. Same thing for Y, we can have 9 possible ways to choose. So therefore the number of combination pairs will be 9 times 9, which will be 81. Right, let me just rewrite the answer. For part B, find the probability that the greatest integer that divides both of the chosen numbers is a multiple of 2 and not a multiple of 2. So what it means by the greatest integer that divides blah 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 is the GCD of those both chosen numbers. So we can rewrite the GCD as 2 times n for some arbitrary integer n. Now let's just say the chosen numbers will be x and y from each corresponding set. Now for it to have a GCD of 2, both of them must be a multiple of 2. And we don't really care about the rest because n could stand for anything, and these also can stand for anything. What we only care about is that it must be even or it must contain a factor of 2. So how do we do this? Notice that the list of the elements of the list of all elements in X which are a multiple of 2, let me just write that, will be let's say 2, 4, 6, 8, and 10. And the number of elements that satisfy the same criteria, which is a multiple of 2, will be 4, 6, 8, 10, and 12. Notice that if you take any two numbers right here, for example 2 and 10, it will be always guaranteed that the GCD will be a multiple of 2 at least. Next, we can find how many ways such that we can actually find the GCD to be equal to a multiple of 2. Notice there are 5 ways to select a multiple of 2 from X, and there are 5 ways to choose a multiple of 2 from Y. So therefore, the number of ways such that the GCD is equal to 2 is 25. Therefore, our probability that our GCD is equal to 2 will be 25 over 81. And that's just part 1. For part 2, we need to find the probability that the GCD is not a multiple of 2. Well, that's pretty simple. We can just write the probability that the GCD is not equal to 2. Notice that this is exactly equal to 1 minus the probability that the GCD is equal to 2. And this is actually a pretty common probability rule. So a probability of an event happening is exactly 1 minus the probability that that same event cannot happen. So this will be equal to 1 minus 25 over 81, which then will be equal to 81 minus 25, which will be 56 over 81. Here's question 4. The product of two numbers is 4107. If the GCD of these two numbers is 37, find the difference between the two numbers. Alright, so let's just assume that the numbers are x and y respectively. and their GCD will be 37. Oops. Also keep in mind that x times y is equal to 4107. Now for these two numbers to have a GCD of 37, both of them must have a factor of 37. And any other factor, let's assume that those factors are a and b respectively, where a and b are co-prime, or in other words, the GCD of a and b must be equal to 1. Otherwise, assume that the GCD is 2, therefore we can pick a 2 out of here, and then the GCD will no longer be 37. So that's an important thing to keep in mind. So substituting the values of x and y into this equation, we will have 37 times 37 times a times b, which is 4107. This will give us 1369 AB is equal to 4107. That means a times b must be equal to 3. Now keep in mind that we assume that a and b are co-prime, and not to mention they are also integers. The only two integers that when multiplied itself give us 3 would be 1 and 3. And good thing here, they are both co-prime. So we can just set one of these to be a and one of these to be b. Therefore, we can replace each of these to be 1 and 3. What the positions of 1 and 3 could be switched whichever you want. Therefore, our numbers will be 37 and 111 respectively. Therefore, what is the question asking us? The difference between the two numbers, which will be 11 minus 37, which is equal to 74. Right, so here's the final question, question 5. Find the number of factors of 9,000 to the power of 2021, which seems a bit overkill, but we have this hint right here, which says that the number of factors of n, which is expressible as its prime factorization as so. So we have p1 to the a1 times p2 to the a2 times all the way up to pr times a to the r. pr times ar, where p1 all the way up to pr are primes, and a1, a2, and all the way up to ar are all positive integers. So if n is expressible as its prime factorization as so, its number of factors is the product of its powers plus 1 as shown here. So it's a1 plus 1, a2 plus 1 times all the way up to ar plus 1. Or it can be expressed as this product right here. Alright, first what you need to do is to express 9,000 as its prime factorization. Notice that 9,000 could be rewritten as 2 to the third times 3 squared times 5 to the third, all to the power of 2021. And by using index formulas, we can actually distribute this 2021 and then multiply it by each of these powers right there. So we will have 2 to the power of 6063 times 3 to the power 4042 times 5 to the power of 6063. So the number of factors by using our formula above will be 6,663 plus 1 times 4042 plus 1 times 6,063 plus 1. Now let you guys go do this in your calculator, because judging by its numbers, it is very big. So it turns out that the number 9000 to the power of 2021 has way too many factors. And that concludes this video, so I'll let you guys do the arithmetic right here. So hopefully you guys enjoyed this. Please subscribe for more videos, and I'll see you guys in the next one. Goodbye.